So I look back and realize I have actually never made a video about chain rule, and definitely need some of that in there because it is one of the more significant topics of calculus that has a lot of different pieces to it. So I'm going to try to keep this first video relatively short. I just am going to have about 5 questions that I'd like to go over, and I'm going to go over it in a very specific way, which is not necessarily the long-term way I'm going to handle this, but it's more of a developmental view of the topic. And I'm borrowing problems directly from the course that my son is taking at Butte College. These are some of the problems that he was asked to address. So the first thing that happened in that set is we were asked to take these problems right here and turn them into a composition and therefore take that derivative of that composition. So if you look at this particular problem right here, if you were to view this as a composition, this would right here would be that interior function. So what I did is I said, well, let's let u be x squared plus 10, excuse me. Now, if that's the case, then this original function right here would be u to the minus 5. That's what y would be in a sense on that particular problem. So if you put those two things together, that composition would work. So you could call this k of u, if you will, or y. Maybe I'll put a k of u in front because clearly k of u means you're going to plug this into there. Now, the derivative of u, we've changed something a little bit here. And so when I take the derivative of u is now being compared to x. So its derivative, instead of calling it dy dx, because it's not y, it's u, it would be du dx, would be 2x. Now over here, y prime, which is really y being changed with respect to u, because y is related to u, we'd have negative 5u to the minus 6. And I'm just simply employing a quick power rule. Both of these derivatives are independently very, very simple to create. And, we talked about how people rejected Newton's first ideas, but they really liked Leibniz views. And this is one of the reasons people like Leibniz look. Because Leibniz just said, well, look, if you take du dx and you multiply it by dy du, notice that those du's look like they would just cancel out and leave dy dx. And although there is a slight fallacy of logic there, it works remarkably well. And the reason why I said it's a fallacy is it's because the rate of change of u with respect to x, meaning like how do u and x interact with each other? Like making a small change in u, what effect does that have in x? Making a small change in y, what effect does that have in u? Well, these change rates are not going to be identical, but keep in mind we're looking at infinitesimally small values. And honestly, they do cancel out. That's just sort of what happens. And it's not technically true, but it just works. And so this is kind of what people do is they set them up so those things would cancel out. And so dy dx is simply the product of du dx right here and dy du right there. So I usually write the second piece first, and so I usually do the dy du portion first and the du dx second, even though I wrote it backwards over here. So I will do a little bit of simplification. Negative 5 times 2x is negative 10x. And of course, this is u to the 6th power, where u was something I made up, where I said, let u be x squared plus 10, and I am out. Okay, now, for our second problem, very much like the first, if we went ahead and decided to say, let u be the interior function x squared plus x plus 1, then du dx would be 3x squared plus 1. Now, in that way, I would say then that y would be then u to the 4th power, or now dy du would be 4u to the 3rd. Again, quick power rule. You notice one of the benefits of this chain rule thing is you're just taking a hard problem and you're turning it into 2 independently very easy problems. And then, of course, dy du times du dx would in fact be dy dx if we think about that. So there we go. Dy du is 4u cubed times 3x squared plus 1. And of course, we could have substituted already for what u is, because u was a creation of my own, just to simplify the problem. But I'm going to replace the u right here with this original u right there. Now, Here's something that I would say, I mentioned in the intro to the video that this is really not the way I do these problems myself. In the long run, we're going to start doing things faster, as we often do in mathematics. We had a formal way for you to do slope, and then we're like, yeah, dy dx. So the way I kind of look like this is I look at this as like Bob to the fourth. Well, if you do Bob to the fourth, it'd be 4 Bob to the third d Bob. Now, again, that's going to seem a little bit strange, but what I'm saying is if you could think of h of x, this guy right here, being the composite of two functions, if you kind of follow what happened, take a look at f, which is all of this ugliness to the fourth. What do you see over here is it's all of this ugliness to the third power. So it becomes f prime of g of x. So that outer function got stripped down according to that rule by 1, but then right inside the function that would be the interior function g, which is right here, pops right there. So we multiply it by g prime. This is the way most people look at that problem, and I'm going to use that in one of my upcoming questions. So if we are going to do this problem right here, again, let's let u be x cubed plus 2x, making du dx 3x squared plus 2. That, of course, means y would be e to whatever that power was, which was u, so dy du would be e to the u. So that makes dy dx the product of these two things. So the product of those two things would be dy du, which is e to the u, times du dx, which is right here. Again, that exponent being x cubed plus 2x. But again, you still have that same thing, but the derivative of e to Bob is e to the Bob d Bob, which is you're going to take the derivative of that other piece. So that's going to be helpful as we go through more complicated problems down the line. So I just have 2 more that I was going to look at with you that I thought were pretty decent little problems. Got to see where I put those problems because I had them ready. Here they are. So a little bit of a different view. So suppose h is f of g. Now, as I mentioned a second ago, h prime of x in a composite is the derivative of the outside function times the derivative of the inside function. That's just a rule that we'll have memorized. We do it over and over. Each of those 3 examples was an example of that idea. So if we want to specifically evaluate it at the number 3, then I would like to take f prime of g of 3 times g prime of 3. Now again, all I'm doing is I'm plugging in the number, but then we have some information. Up here, it tells me that g of 3, see this? G of 3 is given to be the number 4. So I could change this story to saying f prime of 4 because I just substituted that value in. It similarly informs me that g prime of 3 is 5. So I could replace that number with the number 5. It's just a little substitution method. But then the last little piece of that story says that f prime of 4 right here was given to be negative 10. So I've got negative 10 times 5, which is negative 50. So it's just a question about being able to take a simple rule and backfill that rule based on what we're given. Now, here's our last one. Now, I have a graph. So again, instead of giving a bunch of data values, I have a pictorial representation of the data. So again, as previously stated, h prime would be the derivative of the outside function times the derivative of that inside function. And I specifically want to know what is h prime of 4. So let's see. H prime of 4 would be f prime of g of 4 times g prime of 4. Now, interestingly enough, the thing is g prime is the rate of change of g at 4. So if we go out here and we look at g here at 4, what I see is a simple line that has a rise of 1 and a run of 4, which means the slope of g is 1/4 wherever. It doesn't matter if it's at 4 or any other value. This number will be 1/4, which again, I got because g prime is just the slope of g. Now, We do have something else though, because this says f prime of just g of 4. So if we go over here and we find g of 4 right here, I feel like I have something that's just a little bit off. Let me double check my notes. G of 4 itself, yep, I had it off just a little bit, was supposed to go through the coordinate 4, 5. I was afraid that happened. I just got myself off just a little bit when I wanted to put this there. So according to my graph that I have on another piece of paper, if I plug in G of 4, the graph is supposed to go through 4, 5. So then all I have left to do is I want to take the product of f prime of 5, which is the slope of f evaluated at 5. But again, that's not a big deal because as you go through it, this graph drops 3 and runs 6. It drops 3 and runs 6, which means I don't care where you are on that graph. This has a slope of negative 1/2 times the 1/4 that we've carried over from that other portion. So in this case, h prime of 4 would be negative 1/8. And I'd almost say it wouldn't matter where we go, except you'll notice this one portion of that graph actually does specify a given value. So anyway, that's kind of how you do a little bit of chain rule without going too long. I will post some other videos with a little bit more robust look, and I probably will not use the Leibniz notation of dy dx and du dx and all that kind of stuff very much more. I'll probably jump to a slightly faster version, but I'll see you back for that one. Bye-bye.